Assalamualaikum warahmatullahi wabarakatuh. Today, we from group 17, we will present about the application of fluid mechanics in aerospace engineering. Our team, first is Hanis 220180, and then Zakri 220170, Shazwani, and last is Wangdu Sam. Okay, what is aerospace engineering? Aerospace engineering is the primary field of engineering concerned with the development of aircraft and spacecraft. It has two major developing branches. First, aeronautical engineering, and second, aeronautic engineering. The word nautical means ship. Okay, this is the aerospace engineering. And ada has two type, two major, aeronautical and astronautical. Okay, how can fluid mechanics apply in aerospace engineering? Fluid mechanics successfully help aerospace engineers to build machines that can fly in the sky and even outer space. There are many examples in this world of aerospace engineering that can relate to fluid mechanics, especially an aeroplane. Okay. Part of an aeroplane, such as wing engine, is designed to provide maximum efficiency for aeroplane to fly in the sky.
Winglet of aircraft. A winglet is a device that deals with the features of airflow and its effects. Importance of the technology. Winglets are vertical extensions of wingtips that increase the fuel economy and cruising range of an aeroplane. Winglets, which are designed as a miniature airfoils, lessen the aerodynamic drag associated with vortices that form at the wingtips as the aeroplane passes through the air. Reduced wingtip drag reduces fuel consumption and increases range. Another possible advantage of winglets is that they lessen the strength of wake vortices. Those trail behind the jet and pose a risk to other planes. These variables heavily influence the minimum spacing requirements between aircraft operations at airports. Basic operational theory. Winglets are designed primarily to improve the overall efficiency of aircraft. A winglet is a device designed to increase aircraft economy by reducing lift-induced drag created by wingtip vortices. At the tip of its wing, there is a vertical or angled extension. So here the figure of wingtips vortices. Benefits to human. First, it reduces the fuel cost. Second, winglets boost airline earning or lower passenger rates. Third, reducing environmental impact. Disadvantages. Though winglet of an aeroplane provide benefits, it does have disadvantage, which is increases the chance of getting hit at the side of the aeroplane. Designs. Blended winglets. So we can see the figure of blended winglet here. Second, wingtip fans. Winglet of this variety extended from the wingtip in both directions, outward and downward. So we can see outward and downward. Next design is racket wingtips. Racket wingtips appear to be simple wingspan extension, but they have a greater degree of sweep than the rest of the wing. So we can see the record wheelet here. Specification: wheelet geometry. First, wheelet aerofoil. The wheelet aerofoil can be the same as the wing, or it can be modified to meet the requirements for lift and drag. Wheelet height. The optimal effected drag and profile drag relationship are controlled by the wheelet height. Third, twist or sweep. The twist sweep angle has a similar effect on the wheelet and tailors the load distribution. Next, toe angle. The toe angle governs the total loading of the winglets. It has an influence on the load distribution on the wing and is suited for a single flight condition. Next, chord distribution. Small chord distribution requires a high coefficient of lift, whereas when the chord distribution is too large, the load of the winglet causes the outboard part of the wing to stall early. So we can see the figure of specification wheelet geometry.
Aerofoil wing. What? How airplanes fly. Airfoil is a cross-sectional shape designed with curved surface that produce bigger lift but small drag during flight. There are two main forces that act to the part, which is the lift and drag forces. The importance of airfoil wing is it is highly efficient lifting shapes, able to generate more lift than similarly sized flat plates of the same area, and able to generate lift with significant less drag. This is how planes fly. The basic operational theory: first is the lift. Lift is the force that the wind exerts as it passes through over the bonnet of the wing. Next, the weight. Weight is the result of gravity's downward pull. The force that propels an aeroplane forward is known as thrust. When the engine rotates the propeller, thrust is created, and drag is resisted by the forward-acting force. The drag slows the aircraft and restricts the forward thrust speed. There are actually four main forces that act to the wing, which is the lift, weight, thrust, and drag force. Benefits of human life: a thick airfoil creates more lift than flat airfoil at the same speed, and it gives low takeoff and landing speed. A thick airfoil can accommodate large fuel tanks and landing gear. Commercial aircraft will use an airfoil that is optimized for cruise flight in terms of lift and drag. They will extend the flaps when they need to slow down and land, which increase the camber and bigger wing area. The stall speed is lower, but the drag is high, making landing safer. This is the design and specification of airfoil wing. The shape and design of airplane wings are typically determined by the intended use. A thick airfoil is most effective for low-speed flight, whereas a thin airfoil is more effective for high-speed flight. Airfoil is typically fall into one of two categories: conventional flow and laminar flow. The laminar flow airfoil greatly reduces drag since it requires less energy to slice through the air. Aspect ratio is defined as the wingspan power of 2 divided by the area of the wing. High aspect ratio wings have skinny and long spans, but low aspect ratio wings stubby and have short spans. A higher aspect ratio, the lower the drag and slightly higher lift. Increase the wing area will increase the lift. Doubling the area will doubling the lift. High aspect ratio has less induced drag because the wing tip has less area. The relationship of fluid mechanics and aerofoil. There are two main relationships, which is the Bernoulli equation and the Euler equations.
Hi everyone, I'm 2200147 Wongdu Sam, and I'm going to present about aero engine and how fluid mechanics apply in this subtopic of aerospace engineering. Now, I will explain about the turbofan engine basic operational theory, which is most commonly used by commercial aircrafts. Firstly, air is being sucked in and it goes two ways. The first way is to bypass the combustor, compressor, and turbine. For the second way, it goes into the compressor, combustor, and turbine. For the first way, the air is sucked in and bypass the propulsion system and flow through a narrowing duct to produce a high velocity at outlet. For the second way, the air is first compressed by low pressure compressor. Then it is further compressed by the high pressure compressor before being combusted in the combustor. The combusted air will then flow to the high pressure turbine. Lastly, the air will flow from high pressure turbine to low pressure turbine before exiting through the nozzle of the exhaust. In this slide, I'm going to show the comparison in design and specification of a turbofan engine. In a conventional turbofan, a single shaft connects the fan, the low pressure turbine, and the low pressure compressor. In this configuration, the maximum tip speed for the larger radius fan limits the rotational speed for the lower pressure shaft and thus the lower pressure compressor and turbine. At high bypass ratios, the tip speed of the lower pressure turbine and the lower pressure compressor must be relatively low, which means extra compressor and turbine stages are required to keep the average stage loadings and therefore overall component efficiencies to an acceptable level. Lastly, how can fluid mechanics apply in this turbofan engine? We know that every action has an equal and opposite reaction force. The imbalanced force created by the air in the backward direction causes the airplane to have a thrust force forward. To move an airplane through the air, thrust is generated by the propulsion system and the bypassed air. The main equation of the thrust is F equals to the thrust of fan plus the thrust of core and plus the product of the bypass ratio and the core mass flow rate and the fan velocity. The equations to get the values are as shown in this slide. That is all from me. Thank you.